1, 2, 3, and go. There are a ton of really amazing speakers today, and I'm happy to have a slot in such an excellent lineup. Of those talks, I did a quick count of HashiCorp products mentioned by name in the titles of those talks, and 21 mentioned Terraform, 13 Vault, 5 Nomad, 4 Console, and 1 Packer. And of course, many of those Terraform talks also have Packer content. Acting behind the scenes in every single one of those is a piece of technology called HashiCorp Configuration Language, or HCL. I'm Russell Rollins. I'm a release engineer at HashiCorp. And today I'm going to talk about using HCL2 to build what I'll refer to throughout this presentation as domain-specific configuration languages. That's not really an official piece of terminology, but I think it's kind of a useful way to think about HCL. HCL configurations and applications that parse them are not generic. There's a syntax and logic built into the configuration itself in a way that we wouldn't see in a more generic tool like YAML or JSON. And why intermediate? In my opinion, there are a lot of resources in the world for getting to hello world with HCL. There's a lot of good information around level 1. Because HashiCorp tools are open source, there's also a lot of code available at the highest levels of complexity. The Terraform source code is right on GitHub, and no small part of that code is Terraform's engine for parsing HCL in .tf files. There's a lot of information around if you're operating at level 10. But for people like me, who are starting around level, say, 2, and want to move to level, say, 7, I think there's a lot of good learning to do, but not as many resources for it. A lot of the resources are at the extremes. But before we go any further, let's take a look at a motivating example. This is a snippet from a real deployment manifest used to configure how a service is deployed to Terraform Cloud. Example project, despite having the word example in its name, is actually deployed all the way to production and serves as living documentation for how to onboard new projects into our deployment system. For this HCL configuration, the domain we are specifically configuring is deployments. These manifests are written in HCL, and they use many of the concepts we'll use today. The two callouts here are some of the ways we use more advanced concepts in HCL. env.buildID is a variable, and it's manipulated from the environment. We gain a useful measure of safety here. If it was not set, this would throw a prominent and clear error rather than containing an empty string. The artifact block shows another useful technique. It uses a sort of polymorphism where different types of artifact have different config blocks. In our case, this is a Quay repo, and it has a repo and tag in the config. But if it was an S3 artifact, the config block would have entirely different configuration options. By using partial decoding of HCL, we can still have some type safety on this config block, despite the fact it isn't clear on the first decode pass exactly what type of artifact this is. Since this talk is aimed at people who hopefully have some experience with HCL, I'm not going to spend a ton of time doing theory or explanation of what HCL is, but I do want to start by pointing out some high-level differences with other tools. When we compare HCL to something like YAML or JSON, we could see a few standout differences. HCL has a schema, and it easily supports variables and functions. We don't need to add an external templating library, such as Go's, or use a tool like JSON. All that's built into HCL itself. The point I want to make here isn't that other tools are bad, but that HCL differs from them in a key way. Generally, configuration files in other languages are generic. YAML is YAML is YAML. Your application might not be able to consume the input YAML successfully, but if it can decode one YAML file, it can decode another. HCL configurations, on the other hand, are domain-specific. Loading Terraform files as Nomad jobs isn't just a bad idea, it's impossible for Nomad to parse. When your application consumes HCL, It operates closely in tandem with the configuration file, forming a domain-specific configuration language. You aren't just parsing a generic file, you're building a little language for your own use. Some of those languages aren't all that small either. There are no less than 100 functions supported in Terraform HCL files. This idea is very similar to other domain-specific languages you might see in different programming contexts. We're just applying that idea to configuration. Think of how verbose technical manuals sometimes need to be. They must be able to communicate complex ideas to readers who start with no shared context with the writer. It's very different than how you might communicate in code snippets, acronyms, or jargon with a coworker. When communicators share context, they can speak in information-dense ways that might be impenetrable to outsiders. HCL is jargon that you speak with the application being configured. Because of shared context, you can communicate more complicated ideas in short ways. This is possible in a more general language like YAML, but there isn't an effective way to guarantee that shared context. When you write a YAML file, it looks the same as every other YAML file. So it's hard to know if it might be a dialect your parser can't speak. This jargon idea is analogous to what I've been calling a domain-specific configuration language. It's all about shared context. When you work with Terraform, you know that you're configuring Terraform. And when Terraform reads an input file, it knows those input files are intended as Terraform files. I've built a toy example that I'll demo next. It's simple, but already some of the power that HCL enables is starting to show itself. It uses 3 distinct techniques for creating a domain-specific configuration language. So let's give them a quick once-over before we get started. Variables allow a piece of configuration to be more dynamic. We can create HCL configuration files that easily work with concepts, such as 12-factor apps, by loading configuration from the environment. We can think of other pieces of configuration that are specific to the environment, such as the AWS Instance Metadata Service. You might be able to create variables that automatically make the region or availability zone available to you. You could also include variables that are specific to the process calling your config file. For instance, you could have the process ID of the process parsing the config file as a variable. Functions make this configuration even more flexible by bringing in arguments. Functions might be used to represent manipulations of input data or to work with external services. Whether you're manipulating strings or querying another service, functions can allow more information-rich configuration files. Partial decoding allows for one bit of HCL to reference another. One application of this technique is Terraform variables, which allow blocks to reference each other. Terraform needs to be able to partially decode an HCL configuration to allow the variables defined in one place to be referenced in another. We'll use a much simpler application of this technique to allow polymorphic blocks that will all be pets, but are further subclassed into dogs and cats. So if I have to listen, So if I have to listen to myself talk anymore, I'm going to start getting bored. So let's take a look at some code. Here we see an example configuration file. It makes use of variables such as env.catSound to adapt to its environment. We can also see that the cat's attitude changed. We've used the random function to encode some of our domain-specific knowledge about the fickleness of cats. We've also built some polymorphism into the pet block. Cat and dog type pets have different configuration characteristics. If we add the wrong characteristic to the wrong pet type, we get an error. And this has some additional type safety built around it. We can't add an invalid pet. So since we're not built to handle fish, it gives us a helpful error. Let's take a look at the code that powers this, starting with the pets HCL struct. We can see this structure has the basic fields for a pet, name and type, as well as a characteristics block, which is where our partial decoding takes place. Notice the use of comma remain decoded into an HCL body. Using comma remain, you can decode HCL into an HCL body or HCL expression that can be further decoded after you've done other logic. In our case, after we switch on pet type. Notice the cat struct only has the sound field. And the dog struct only has the breed field. So let's dig into the body of our logic. We open a file, by default, pets.hcl. We read it into a byte slice. Now, the real HCL logic comes in. We send those bytes to a new parser that we create. Next, we create a context. Contexts are used by HCL to add variables and functions. So let's take a look at this helper function and see how those are implemented. Variables are created as maps of string, the variable name, to cty value. Cty is a package that defines a customized type structure. It's used under the hood by many HCL utilities. We'll keep things fairly simple here. In order to use nested variables, we first define an object val, then we define strings. This allows us to access variables at env.variablename. In our case, env.catsound. Functions are built similarly. A map of string function name to cty function. Cty functions are a bit more complicated, so let's break it down field by field. Params is a list of required positional arguments. For this implementation of random, there aren't any. var param is used to allow a var args type input. Here, we've restricted it to strings. Type defines the return value. Random always returns a string, but other functions might return different types depending on the inputs, and that could be built here. Impl is where we actually define our function. In our case, by selecting a random input and returning it after some type coercion to match our type guarantee. Okay, let's get back to the main function. We now decode all the defined pets into a generic form. This is the partial decoding step that leaves undecidable HCL bodies in characteristics HCL. Now we implement the switching logic that decodes cat HCL bodies into cats and dog HCL bodies into dogs. We avoid invalid pet types with a default case as well. Finally, we return. To dig into these concepts a bit more and give you some ideas to think about for your own domain-specific configuration languages, let's take a look at some branches I've made. Cat sound is now a required variable instead of having a default. This is because now, instead of hard-coding environment variables, we're loading them by grabbing anything that starts with ps underscore for pet sounds. So we could easily add a new variable to the env object. This technique might be useful when you want to load many environment variables, but want to avoid collision with other tools. For instance, when you're working with common environment variables like AWS credentials. So let's take a look at how it's built. Now, instead of having hard-coded environment variables, we range over the entire environment, check if the environment variable starts with a known prefix, in this case, ps underscore, removes that prefix, and then saves it to our cti string value. Let's beef up our function as well. As you can see, random now has two positional arguments, a count of how many items to select, and a separator to join them with. Now we can make our cats even more fickle, or we can make our dog pet a mix. So let's take a look at the function definition and see how we did. The big change is that we now have required positional arguments. These have names and types that make them easier to use with helpful error messages. So we can't use an invalid type. The var param and type are the same as before. Impl now loads the count and separator from their input arguments. After doing a bit of type coercion to make them easier to work with in Go, we now also have an error return. In this case, it prevents us from returning too many values from a short list. This returns a nil val and a Go error. Finally, we join everything together and return a C tie string value. I'll end with a pretty simple call to action. You should go out there and try this. Nothing will teach you quite like firsthand experience. So if you're working on a CLI tool that takes an input file, like Terraform, or a service that needs a configuration file, like console, consider building it in HCL and bake some of your expertise and domain-specific knowledge into the config itself. HashiCorp has been doubling down on our use of HCL with huge improvements to the language in HCL2 and Packer 1.5 adding HCL support to Packer as well. HCL is part of the secret sauce of HashiCorp products, but it's also all open source and PL2. I'd love to see more of it out in the wild.